Okay, so guys, what you're gonna do to start, over on the side counter are the 3 handouts. So all 3 of these that I talked about yesterday, the do now, the free response packet, and the review are on the side counter. So what I want you to do, and I did on your own, just so that way you can kind of see what you know, what you might need to review. I'm gonna put a timer up on the board for 7 minutes. I'm gonna set a timer for 7 minutes. So the do now free response is the single page. So it's the single page, says 2019 on one side with number 1. Number 2 says 2017. And I'll put 7 minutes, and I want you to work through the question. So each side of the page is different. So the front is number 1, back is number 2. I just want you to try them. All right, take a guess. It's in class, so if you make a mistake, it's easy to fix. And then we're going to actually go over the scoring guidelines. So what I'm going to do is I'm going to go ahead and put the countdown up on the board. So you'll see 7 minutes to work through the 2 questions, and then we'll go ahead and go over the scoring guidelines. Once this time runs out, we'll also then do a review before the quiz. So first period, the way that it works, we went through this, we did the review, and then during the second period of class, they took the quiz. Probably the actual free response packet, the free response questions themselves, we will probably get to tomorrow. So take about 6.5 minutes now, work through these 2 questions. If you finish and you still have mastering to do and you want to spend the rest of the time working on mastering, you can. And then we'll go through the scoring guidelines and everything for these questions. So as always, free response, you get a periodic table, equation sheet, calculator. And then you can use your notes and stuff too. A lot of people in first period were adding to their notes as we were going through everything. I would recommend as we go through the scoring guidelines, if you don't have your notes out, it might be worth having your notes out to add information to, especially because these 2 questions, I mean, these were 2 questions from the 2019 and the 2017 test. So these are old AP free response questions. Okay, so that was 7 minutes. Was this a little bit more time? Maybe. But what we'll do is we'll go through the scoring guidelines. So this first question was number 6 off the 2019 test. Now, somehow when I put this into Google Docs, I converted the Word doc to Google Docs. I didn't realize that it actually cut off part of number 6. So you have parts A and B. There was actually a part C. I didn't realize it cut it off until I was going through the scoring guidelines today and was like, where's the rest of the question? So I'm going to show you part C. It's still kinetics. It'll be a good review, but that way you can see the whole question. So number 6 off of the test 2 years ago, so the last time we had an in-person AP test, number 6 was all kinetics. So questions 4, 5, 6, and 7 on the AP test are considered short questions and they're worth 4 points. So you'll see exactly how this was scored. So this question gives you a balanced equation up here, and it says that nitrogen dioxide is a byproduct of the combustion of fossil fuels. Here's the decomposition reaction. So you have the reaction up here. So this is important because this tells you that NO2 is the reactant. Then it says that the concentration was monitored, and you have these three graphs. So you have concentration versus time, 1 over concentration versus time, and natural log of concentration versus time. So it's really important that you're paying attention to the y-axis because it's not in the normal order that we see. So part A, explain how the graphs indicate that the reaction is second order. So it's telling you it's second order right here. Part A wants you to explain how you know. Well, the 1 over concentration versus time graph was a straight line. That's it. All right, for part A, the 1 over concentration versus time graph gave us a straight line. That was 1 point. And then part B, so this was the only other part that you had on the do now sheet. Part B says write the rate law for the decomposition. So remember that rate law is always rate equals K times concentration of reactants. And then it's raised to whatever order that reactant is. Part A told you that it was second order. So that means that your exponent is a 2. So rate equals K times concentration of NO2 squared. That was it for part B. So that was the second point. Now part C, this is what was not on the do now. This is what got cut off. But you can kind of read through up here and I'll talk through it. So it says consider the 2 possible mechanisms. So you'll notice they gave us mechanism 1 and mechanism 2. Part 1 of C says is the rate law described by mechanism 1, shown below, consistent with the rate law you wrote in part B. So in part B, we wrote rate equals K times concentration of NO squared. So part 1 wants to know, is this mechanism consistent with that rate law? Well, remember when you have a mechanism, the rate law is based on the slow step. The slow step is step 1. So rate equals K times the concentration of NO2 squared. There are 2 NO2s, so it's NO2 squared. So our answer would be yes. All right, answer the question first. Question is the rate law consistent? Yes. Then we give our justification. Step 1 is the slow or the rate determining step. So the rate law is based on the slow step, which is rate equals K times NO2 squared. Part 2 is the rate law described by mechanism 2, consistent with the rate law you wrote in part B. Well, now notice that the slow step is the second step. So if we write the rate law for the slow step, it's rate equals K times the concentration of N2O4. Well, remember that an intermediate cannot be in an overall rate law because we can't find the concentration. So we use the fast step. Remember, treat this like an equals. So NO2 times NO2 equals N2O4. And we plug in for N2O4, which is NO2 squared. So our answer for part 2 is yes. Step 2 is slow. So we write the rate law based on the slow step, which is rate equals K times N2O4. But because N2O4 is an intermediate, we have to plug it back in, which is NO2 squared. So part 1 and part 2 were each 1 point. But that was the part that got cut off of the do now. So dealing with mechanisms. Remember, with a mechanism, the rate law is based on the slow step. So now number 2. So this was just part of a long question on the 2017 test. So this is on the back of the do now. All right, this was part E. And I'm going to come to the actual free response page itself so that we can look at this data before we look at the scoring guidelines. So for number 2, a student is studying a reaction and they collect data. So they give us time versus concentration, and then the graph that they give us is concentration versus time. So when you're dealing with concentration versus time, we're looking at integrated rate laws. We're looking at concentration versus time, or ln versus time, or 1 over versus time. So for this, it says the student proposes that the rate law is rate equals K times the concentration of CONH2. So this is first order. There's no exponent, so it's assumed to be a 1. Part 1, explain how the data supports the student's rate law. So first, the student's rate law is first order. So really part 1 is asking, how does this data support a first order reaction? So some things I want you to keep in mind for a first order reaction. Half-life is constant. The slope of ln concentration versus time would be constant. Right? The slope would be constant. It's a straight line. And that's about it. The biggest thing is half-life. So here's what I want you to look at on this graph. And if you didn't mark it, or you could mark it as we're going through. Let's look at the half-life of this. When you are given concentration versus time, that is the graph that you can use to determine half-life. Not ln, not 1 over, but concentration versus time. So I have 0.1, that's my initial amount. Half of 0.1 is 0.05. So if I follow 0.05 over to the curve and down, it's 10 hours. So to get from my initial amount to half of that takes 10 hours. So the half-life is 10 hours. Let's look at another half-life. Half of 0.05 is 0.025. So 0.025 maybe here. Follow it over and down. Another 10 hours. Half of 0.025 is 0.0125, so somewhere maybe around here. Follow it over, down, another 10 hours. So the half-life is constant. The half-life is 10 hours throughout this entire process. The fact that the half-life is constant tells us that this is a first-order reaction. So when you are given concentration versus time, if you're trying to figure out if it's first order, look at the half-life. If the half-life is constant, it's a first order process. So if we take a look at the scoring guidelines, this was 1 point, right? From inspecting the graph, we can see that the half-life is constant, which indicates a first order process. So this was a constant half-life, which results in a first order process. First order reactions are the only ones that have a constant half-life. And then part 2, using the proposed rate law and the student's results, determine the value of the rate constant. Include units with your answer. So we cannot use rate equals K times concentration of the urea. We can't use that to calculate K because we don't have the rate data. We don't have a data table that is rate versus concentration. So we can't plug anything into the rate law. Instead, we need to use the information that we have, which is time versus concentration. Time versus concentration allows us to use the integrated rate law if we want, or we can just use the half-life equation. Since it's first order, we can use the half-life equation for a first order reaction, which is half-life equals 0.693 over K. Or if you manipulate, it would be K equals 0.693 over T1/2. So 0.693 divided by 10 hours gives us 0.069 per hours. So this was 1 point for having the value and the units. So you have to make sure you're paying attention to the time units. It was hours, not minutes or seconds. So what they did in the second part here, if you wanted to use the integrated rate law, is they picked points from the table. So the initial amount was 0.1. And then they picked 0.05, which was the amount after 10 hours. So they said, if I have an initial concentration of 0.1, what's the value of the rate constant if I have 0.05 molar after 10 hours? And they plugged it in to the integrated rate law for a first order reaction and solved for K. Is half-life easier to solve for? Yes, probably. But you could use the integrated rate law for a first order reaction as well. The biggest thing with this, the reason that I put this question on here is for part 1. Using the idea that you can look at half-life to figure out if it's a first order process, because half-life is constant. Okay, any questions on either number 1 or number 2? I did put these do nows and the scoring guidelines. They're up on the class website. So on the class website, ptapchem.com, under Unit 5, if you click on the review tab, there for response, and then there's a lot of the review stuff as well. So this is all there if you want to ever go back and take a look at it. All right, so what I'm going to do next, I'm going to show you what we're going to look at today, give you, maybe you'll consider it some good news regarding mastering, and then we're going to actually review for the quiz. So let me share this with everybody in Google Meet as well. So for class today, so we have all of the do now information. So you either could have answered this on your do now sheet, or on your do now sheet you could just write FRQ and be fine as well. So for class today, we will be going through a review. So I made a Kahoot, 15 questions, just to review the concepts that you'll see on the quiz. The quiz is pretty much conceptual. It's all multiple choice, so you're going to see a lot more conceptual questions because usually the math is more free response. Then I'll take the quiz. So the quiz is timed. It times when you open the quiz. It's through ZipGrade again. And so you'll take that. First period, we didn't really have much time to start the free response questions, so we'll just work through those tomorrow. That's where we'll look at a lot of the math, all old or practice free response questions. Here's the big thing, mastering. So since tomorrow is a 2-hour delay day, I had mastering originally due at 7:30. I know this isn't necessarily a lot of time, but I just pushed it back to the start of school. So since first period starts at 7:30, or normally 7:30, that's why I had mastering due at 7:30. But since it doesn't start until 9:30, I pushed mastering back to 9:30. So it's due at 9:30 tomorrow morning. So it gives you a little bit of extra time as you're working through mastering. Remember that there is that mastering help folder. So I sent that in the chat yesterday. I have it linked in the do now slide right here as well. So remember, you always have access to these do now slides. So I just wanted to do that. You'll see that mastering does have the due date of 9:30 a.m. now. So what we're going to do now is we're going to go ahead and we're going to work through a review Kahoot. So you can either use your phone or your computer, whichever one. Calculator, you don't technically need a calculator, but you can use a calculator, periodic table, equation sheet. If you want to have your notes, just to add in extra information to your notes, you can. After each question, I'm going to just briefly talk through. I might give some extra information. First period said this was really useful, especially in the explanations of the questions. So after going through the questions, they said that it was useful because I was kind of explaining some extra information, and they found that extra information was on the quiz. So let me share the tab. So As you get into Kahoot, you don't have to put your name, right? You can make some random name. Last time we played Kahoot, I had a lot of Mr. Shawls. So you can make up a name if you want, use initials. So you can go to kahoot.it, you can put in the game pin, and as we work through, they all have different amounts of time based on difficulty of the questions. But whether you want to use your phone or your Chromebook, either one works. And if for some reason it kicks you out, the game pin will be displayed, so you can always just get back in to the Kahoot. So I'm going to go ahead and start the Kahoot. Again, I'm going to go through each question just briefly afterwards. There might be some pictures, and I might need to kind of talk through if it's hard to see. So 15 questions. So the diagram is going to show collisions between CO and NO2. The products are going to be CO2 and NO. Which diagram is the best representation? So this shows CO and NO2. But if the products are CO2 and NO, which one of these diagrams is the best representation of the collision that needs to occur? 5 seconds. Okay, good. So let's take a look at this because it was kind of split. So if we take a look, again, this is CO and this is NO2. We need the products to be CO2 and NO, which means to this CO molecule, we need to add an oxygen. So we need the oxygen to collide with the carbon to form a CO bond. And then what it's going to do is the CO bond is going to form, the NO molecule will bounce off, and now we have CO2 and NO. In diagram 2, we have nitrogen colliding with the carbon. We don't want a CN bond. We want a CO bond. So diagram 1 is the best diagram. Okay, so concentration of N2O5 was measured over time. The following graphs were created. What is the order? So here's concentration versus time, ln versus time, and 1/, versus time. Good, first order. So since ln versus time was a straight line, N2O5 is first order. So the following will allow the student to determine the rate constant for the reaction. So we have this concentration versus time graph. Based on the concentration versus time graph, how could we calculate the rate constant? So take a look at this graph. There are some points plotted. So 3 seconds. All right, good. So just in case you guessed, if you take a look, concentration versus time. Well, I have 1 molar to start. If I want to calculate the rate constant, I should probably know what order of reaction it is. I know it's not 0 order because concentration versus time is not straight. So it's either first or second order. Well, if I take a look at this, half of 1 is 0.5. That's 20 minutes. Half of 0.5 is 0.25. That's another 20 minutes. Half of 0.25, 0.0125, another 20 minutes. So the half-life is constant. Constant half-life means it's first order. So since it's first order, if we plot natural log versus time, we can determine the magnitude of the slope, and that gives us K. Something to keep in mind, K, your rate constant, is always a positive number. So for a first order reaction of half-life 45 minutes, what is the rate constant? So notice you're not actually doing the math, you're just showing the setup. So if the half-life is 45 minutes, what's the rate constant? Good. So half-life equation, it says that it's first order. First order, you can use half-life equals 0.693 over K, which means K equals 0.693 over half-life. So which of these changes with time for a first order reaction? So which of these changes with time? Three seconds. Good. So over time, the rate of reaction changes. Remember that the rate of reaction, at the very beginning of kinetics, we talked about how the rate of reaction is based on reactant collisions. Over time, you have less and less reactant. Over time, the reactant is being used up. So you have less reactant, which means less collisions and a slower rate. So over time, your rate of reaction actually decreases because your reactant concentration decreases. Rate constant is constant unless you change the temperature, and half-life is constant because it's a first order reaction. So the diagram is going to show energy profiles for a reaction with and without a catalyst. I want to know which one is with the catalyst. Okay, so if we take a look at this, we have X and Y, right? X is a one-step reaction with a high activation energy. So we have reactants. Here's our transition state, but the reactants must overcome activation energy in order to become products. Y shows a multi-step mechanism. However, every single one of these transition states is still lower than X. The purpose of a catalyst is to lower the activation energy. Even if it creates more steps, the activation energy is still lower. And so since the activation energy is lower in Y, right, every single one of these peaks is lower than X. Y is the one with a catalyst. The purpose of a catalyst is to lower the activation energy. So which of the following will lower the activation energy? Okay, some randomized questions here. Good. So adding a catalyst, the whole point of a catalyst is to lower the activation energy. I do want to point out raising the temperature. Raising the temperature does speed up the reaction, but raising the temperature does not lower the activation energy. Raising the temperature gives the reactant molecules more energy in order to overcome the activation energy. So raising the temperature is going to allow the reactant molecules to have more kinetic energy, allowing more of them to overcome the activation energy. So the proposed steps for a catalyzed reaction are going to be given in a picture. I want to know, what is the catalyst? 5 seconds. All right, so let's take a look at this. Remember that a catalyst is a substance that starts as a reactant and ends as a product. So a catalyst is a substance that is used in a reaction but is not consumed itself. So you start with it and you end with it. And yes, it still cancels because it's on opposite sides of the arrow, but Mn2 plus is our catalyst. We start with Mn2 plus, it's still there at the end. It still will cancel. It's not going to be in the overall reaction because it's on the left and on the right, but because you start with it and you end with it, that's a catalyst. So the data of the decomposition of NO2 to form NO and O2 are given, which rate law is consistent with the data. So this one's a little tricky. I gave you a little bit more time. So they give us concentration versus time, ln of concentration versus time, and 1 over concentration versus time. Hopefully you can at least narrow it down to 2 options, because the other 2 options, we've never seen a rate law that looks like that before. But we'll talk through this after we see all the responses. This is a very common type of question we might see with multiple choice, which on the multiple choice test, they don't allow calculators. So I'll show you how we could do this. Good. So here's how we know that this is the correct answer. So when we take a look at this graph or this data table, so whichever one of these produces a straight line tells us the order. Well, remember that a straight line means a constant slope. So whichever one of these is a straight line is the one that's going to give us the constant slope. A constant slope means that it's changing by the same amount every time. So 0.5 to 0.364 is what, 0.136? So 0.364 to 0.286, that's not 0.136, right? It's changing by different amounts every time. I could tell from 200 to 300, that's only 0.051. So it's not changing by the same amount every time. So it's not 0 order. Well, if I look at ln, I could even look from here to here. That's what, 0.24? Here is 0.2. It's not changing by the same from 0 to 100, from 100 to 200, right? 200 to 300. If I look at 1 over, 2 to 2.75, that's 0.75. 2.75 to 3.5, that's 0.75. 3.5 to 4.25, that's 0.75. So notice how the 1 over concentration increases by 0.75 every time. That's a constant slope. A constant slope results in a straight line. So 1 over concentration versus time will result in a straight line, meaning that it's second order. Second order means we have the exponent of the 2. So mechanism for formation of X is 2 steps. I gave the 2 steps. A plus B yields C plus D. A plus D yields X. What's the intermediate? All right, so I want to know what the intermediate is. 3 seconds if you're still answering. looking at this, A plus B yields C plus D. So D is created and then immediately used up. Created, immediately used up. That's an intermediate. All right, so let's go to the next question. So again, we just have 4 more questions. So a reaction between x2 and y has the rate law, rate equals k times x2 times y squared. What is the molecularity? Good. Termolecular. So there is one X2 molecule and 2 Y molecules. Right? The order also tells us the number of reactant molecules. So this is a termolecular process. Now here's something that I want you to keep in mind with molecularity. More than likely this happened as a mechanism. So this is probably the overall rate law given from a mechanism. And the reason that I say this is probably a mechanism is because it is very rare for 3 reactant molecules to all collide at the same time. A termolecular process happening all at once is very rare, because that means that 3 reactant molecules have to collide with proper orientation and energy in order for the reaction to occur. So more than likely a termolecular process comes from a mechanism. So which of the following shows the correct relationship between concentration and time for first order? So I'll read through this. A is ln versus time. B is concentration versus time. C is 1 over concentration versus time. And D is concentration versus time, but the line goes up instead of down. So what shows first order? ln versus time, concentration versus time, 1 over versus time, concentration versus time. Good. ln shows first order. ln of concentration versus time will be straight line if it's first order. So steps for a catalyzed reaction will be given. What are the intermediates? So what are the intermediates in this mechanism? Good. So the intermediates are what are created and then immediately used up. So Mn3 plus is an intermediate. Mn4 plus is an intermediate. Now from this mechanism, you could also look at the overall reaction. So I could ask you to write the overall chemical equation, and you add up all 3 steps. You cancel out anything that is the exact same. So I can cancel out catalysts. I can cancel out intermediates. And from there, I could ask you, what are the reactants? What are the products? So when you're given a mechanism, you can look at a lot of different things. So nitrogen monoxide reacts with chlorine to produce NaCl. What is a rate law that is consistent with this mechanism? So here you have NO plus NO yields N2O2, which is fast. N2O2 plus Cl2 yields 2 NaCl. That's slow. So which of these, this 2 should be outside the brackets. Right, which one would give the correct rate law for the mechanism? Good. So if we take a look at this, the slow step is the rate determining step. No matter what, the slow step is rate determining. So that would be rate equals K times N2O2 times Cl2. However, N2O2 is an intermediate. When the slow step is the second step, you will always have an intermediate in the rate law. So then you have to use the fast step to plug back in. So if I use the fast step, NO times NO equals N2O2. So plug in for N2O2. So NO times Cl2 means NO squared times Cl2. Last question. The equation represents an elementary step in a reaction. Which is the correct rate law for the elementary step? Good. So the key word here is elementary step, which means you can use the stoichiometry to figure out the rate law. So since you have a 2 as the coefficient, that means that NOBR for this elementary step is second order, which is why you have rate equals K times the concentration of NOBR squared. Good. So that's it for the Kahoot